Hi everyone and welcome to my YouTube channel. So far we have finished the AMGM inequality. We've discussed its theorem, and we discussed also some examples, and we covered many ideas that are crucial in our Math Olympiad inequalities journey. So make sure you have watched the AMGM videos first, and in this video we'll be starting with a new inequality, which is kind of a special case of the AMGM basically. However, this special case is really important, as it will crush many hard inequalities that we will face in Math Olympiad contest in general. This inequality is the Muirhead's inequality. So I hope you guys are excited. What are we waiting for? Let's get started. We're going to provide the statement of the Muirhead's inequality. However, we can't do that immediately. We need first of all to introduce one critical idea that we need to understand before understanding the Muirhead's inequality statement. This idea is called majorization. So first let's talk about that. What exactly is majorization? Let's say we have two sequences. First of all, the first sequence is sorted in decreasing order, and we also have another sequence that is also sorted in decreasing order. Of course, these are just any real numbers. Okay, now we're going to have the following conditions. Condition 1, the sum of the first sequence, of course from 1 till n, is equal to the sum of the other sequence, also from 1 to n. Okay, this is condition number 1. Condition number 2 is also sigma xi, but from 1 till k, this is greater than or equal to the sum of yi beginning from 1 till k. Okay, here, like for values of k, 1, 2, 3, up to n minus 1. You might be wondering why it's n minus 1 and not n. Well, for n actually we already have the equality. So it's basically, you can say also n, but it's just like here. So no need to say it. So if you have these two conditions, then you can say that the sequence xn majorizes the sequence yn. There is a symbol for majorization, yes. It's like this. It's kind of similar to the greater sign, but you have this curve a bit. So now we understand what exactly is majorization. If we have sequence xn majorizes sequence yn, that means having the two sequences sorted in decreasing order, we have the sum of the first terms of the first sequence is equal to the sum of the second sequence, and we also have this thing actually is called the prefix sum. If you're familiar with like programming, they use this a lot, this idea, prefix sum. It simply means that you just start from like x1 till xk, like as a sum. So for example, x1 plus x2, then x1 plus x2 plus x3, and so on. So that just means that the kth prefix sum here is equal to the kth prefix sum from the other sequence. Sorry, not equal, greater than or equal to. So if we have these two conditions, then we know that, as we said, xn majorizes yn. Alright, so now we understand what exactly what majorization is. We can actually provide an example. Let's say maybe something like this. 2, 1, 1. This is one sequence. Another sequence is, let's say, 2. Actually, let's do something like this. 2, 2, 1. Now, I think if I put 2, 1, okay, this will not work. Let's modify it. So let's say 3, 2. Then Now we have the sum is what? Okay, that works. So something like this. Let's see. We have two sequences. Let's say this is the x and this is the y. Is the like who majorizes the which one majorizes the other? So first of all, let's see the conditions. The sum of this one is basically 3 plus 2 plus 1, which is 6, and the other one is also 6. So condition number 1 is correct. For condition number 2, let's see, is it correct? So we have 3 is greater than 2. Okay, good. This is the first perfect sum. Then 3 plus 2 is it greater than 2 plus 2? Indeed, it is. This is 4, this is 5. Then we have, of course, the sum is already the same. So that means that x majorizes y. So the sequence, as we said, x majorizes y. Here you go. So this is one example. Of course, you always have the you need to have these two conditions. By the way, sometimes you might have xn majorizes y, or y majorizes x, or sometimes none majorizes the other. So it's totally normal. It's not like this one is either like majorizes this or this one majorizes this. No, sometimes we don't have any majorization relation. It's totally fine. For example, if we have this is, let's say, 1, then from the beginning this is 5. So the condition broke. Okay, so let's keep that in mind. Okay, so now we understand what is majorization. Let's move on to provide the statement for Muirhead. Okay, so now Muirhead's inequality. Okay, so let's say we have the following sequence. These are positive reals, and let's say we also have two sequences. Xn majorizes Yn. Then we have the following inequality: sigma symmetric a1 to the x1, a2 to the x2, till an to the xn is greater than or equal to sigma symmetric, and we do the same thing but for y, till an yn. All right, so here this idea we already discussed it. Now you know why we discussed the majorization idea. It's because we're going to put these numbers as powers. These numbers can be anything, any real number. They can be positive, negative. They don't have to be integers. They can be even something like half. It's totally okay. But we just need to have the majorization condition, and we also have the other numbers. These are of course positive real numbers, just like when we work with the AMGM. Okay, so the majorization is for the power. Of course, the sigma symmetric. We already explained what is sigma symmetric before in our AMGM lessons, so make sure you have watched that. Of course, when we have sigma symmetric, just a quick reminder, that means we have how many terms here? N factorial. Same thing here, n factorial. So it's a big sum actually. We will see that actually most of the times we really don't care about that. We divide kind of by something. Okay, so right now this is the theorem, the Muirhead's inequality. We're going to, of course, to discuss some examples to make everything clear. So let's start with our first example. Okay, so example number 1. So here we're going to solve some standard problems that are really simple, just to understand the Muirhead's inequality. So we need to prove for positive numbers a, b, c, we need to prove the following inequality. Sigma a square is greater than or equal to sigma ab. Of course, this one we already proved it before in the AMGM lesson. It was super simple. basically you can just show that a square plus b square is greater than or equal to 2ab. If you remember, this is how we solved it back then. However, right now our goal is to practice Muirhead to understand it better. So let's try to solve this one using Muirhead. Okay, so how exactly can we do that? All right, for Muirhead, we already have here the ABC that we need to work on. So we already have the ABC. We just need to choose the powers that represent the LHS and the RHS. So what exactly are the powers in the LHS? Clearly, you can see that the powers, if you want to write them like A, B, C, it's going to be A, 2, 0, 0. Clearly, that's the LHS. So basically, our sequence, the X sequence, will be 2, 0, 0. For the other sequence, here we have clearly 1, 1, 0. So it's going to be just that, 1, 1, 0. Always remember to put it in a decreasing order. Okay, so basically these are the two sequences. Now we just need to show that the left-hand side sequence majorizes the right-hand side. So let's check that. Do we have the conditions? First of all, the sum of this is 2, sum of this is 2, so that's good, they are equal. Next, we have 2 is greater than 1, that works. Then 2 is greater than 2, that's good, 2 greater than or equal to 2. And finally, 2 equals 2, we already have it. Okay, so that works. So indeed, we have this majorization, and hence we can write the following inequality: sigma symmetric a square is greater than or equal to sigma symmetric ab. Okay, now what's sigma symmetric a square? It's easy. It's just sigma 2 times sigma a square, and this one is 2 sigma ab. So simply we can just divide by this 2 by this 2 to get the inequality that we want, and basically we're done. So as you can see, this is a simple application for the Muirhead. It immediately solves this problem without the need to think of the pairing strategy for the AMGM. That's why we said it's really more efficient to apply the Muirhead in such problems. It saves lots of time and lots of effort, so we don't need to go and search for the pairing that's correct. Okay, so that's it here. Of course, we also saw that the idea of symmetric. Remember always that Muirhead is for symmetric inequalities. So you can't show it for like cyclic inequalities. And remember that there is a difference between sigma symmetric and a symmetric sum. So while this is not sigma symmetric, it's sigma cyclic, it's actually a symmetric thing because it has a square plus b square plus c square. So this is a symmetric thing, but it's not sigma symmetric like this. Sigma symmetric is 2 times that. So most of the times actually it's just enough to notice this and we are done. The sigma symmetric here and symmetric there, they simply like vanish because of the 2 and 2. Alright, so let's take another example. So example 2, also something similar. We'll be working with 3 numbers, a, b, c, positive, and we need to show the following: sigma a to the 5 is greater than or equal to sigma a cube bc, and this is greater than sigma a square b square c. Okay, let's see how we can apply Muirhead again. Well, clearly we just need to search for the like the corresponding sequence. So for the LHS, this one here, what is the sequence? It's super easy, 5, 0, 0. For this one here, we can easily see that it's 3, 1, 1, 3, 1, 1, and for this one here, it's just 2, 2, 1. Again, always make sure that you go in non-increasing order, or like kind of decreasing order, but of course some numbers might be equal. So now we just need to show that this majorizes this and this majorizes this, and this is really easy to check. Most of the times, like just check the sum. The sum is the same, so here 5 and 5, and now actually since we have all, like the whole 5 is here and here is 0, so for sure we have the majorization conditions because all of it is here. So 5 is greater than 3, 5 is greater than 4, and that's it. So this one is correct. We have shown this. Now we need to check this as well. So also 5 and 5 here. We have 3, 2, and 4 and 4. So basically it's also correct. So we're done. Of course, we have the same thing. We have actually sigma symmetric, and sigma symmetric, but we can always do it since it's actually just 2 times that. So really it doesn't matter here. This is just enough. So once you notice this, you can just say by Muirhead's inequality and write what you have, and basically just divide by 2. Okay. So now you should be getting the flavor of Muirhead. It's really simple, and it's really it will make your life easy in lots of simple problems. Of course, each one of these problems can be solved with the AMGM by finding some pairing. But imagine that you need to here look for the pairing a to the 5, b to the 5, c to the 5, and like many a's you need to search for. Here we don't even think about that. We just like put this sequence, and apply Muirhead. Okay, let's take another example. This one is from the Canadian Olympiad. So we have A, B, C again. They are positive, and we need to prove sigma A cube over BC is greater than or equal to sigma A. Alright, now we have fractions. Of course, once we have fractions, we have 2 ways. Either we can multiply by ABC both sides to like get rid of the fractions, or we can actually work with it immediately. So let's see how we can work with it immediately. Well, think about it. How can we produce the sequences here? So the RHS is really clear. The RHS is just 1, 0, 0. Easy. But the problem is for the LHS. We have fractions. How can we deal with that? Well, guess what? A cube is A cube, no worries. B, in the denominator, that just means B to the negative 1. And C, also C to the negative 1. And hence, we can simply come up with a sequence 3, negative 1, negative 1. And remember, don't be shocked that we are using negative numbers. From the beginning, we said that in majorization, we don't have any condition that the numbers are positive or anything, right? They can be any real number. So let's just check now the majorization condition. So here the sum is 1, the sum here is 1. Let's check. 3 is greater than 1, correct. 2 is greater than 1, that works. So we're done. The majorization is correct, and hence the inequality is correct when you heard it. Of course, always the same idea. You have the symmetric. You need to do the symmetric first. But the symmetric is the same as cyclic because it's 2 times cyclic right here in these problems, and hence we really don't need to bother ourselves. Okay, so now we're done with that question. Let's solve another one. Now they are also giving us 3 positive numbers, and they're telling us ABC is equal to 1, and prove sigma A square is greater than or equal to sigma A. Alright, so now we have some conditions. How can we deal with that? Now, you might think about Muirhead right now. We'll just say that 2, 0, 0, and here 1, 0, 0. Does this majorizes this? Let's see. The sum here is 2, the sum here is 1. So the first condition is broken. So we can't apply in Muirhead, unfortunately. Well, you need to keep in mind that of course you can't apply Muirhead. If we can apply Muirhead immediately, then the condition is useless. So we need to use the condition somehow. Remember, we discussed in our previous videos how we can deal with conditions like that. And we said we introduced a very, very powerful idea that was homogenization, right? So let's do homogenization here to get rid of this condition. So how can we homogenize this? The LHS is degree 2, the RHS is degree 1. So let's add another degree 1 here to make a degree 2. How can we do that? We can simply here put ABC. because it's 1. But of course not ABC, because we will add this by 3 then. So we just actually multiply by cubic root of ABC, right? Cubic root of ABC will be good. So that means this is the same as showing this. Sigma A times cubic root of ABC. Guess what? Now, if you think about it, now of course we're done with the condition. We can forget totally about ABC equals 1. Now we just need to show this inequality. Now if you think about Muirhead here, it's 2, 0, 0. But what about the RHS? How can we handle roots here? Well, A here is A to the 1, but here, what is it exactly? Cubic root of A? Well, simple. It's just A to the third. So now we have A to the third times A. So that means it's A to the 1 plus third, right? 1 plus third is just A to the, we can just write it like this, 4 over 3. Same thing for this, for B, and for C. And because of that, that just means that we can now create the sequence 4 over 3, third, and another third. And guess what? Let's just show that this majorizes this. Let's check. The sum here is 2, sum here is 2. Good. 2 is greater than or equal to 4 over 3. Correct. 2 is greater than or equal to 5 over 3. Correct. And hence, indeed, we have the majorization. And hence, the inequality holds. And hence, of course, our original inequality holds as well. Alright, so that's really good, because that means that we can apply Muirheads for powers that are positive integers, negative integers, even like other real numbers, right? Anything. So always don't bound yourself to only positive integers. You can always apply Muirhead for all of these things, as long as you can write it as sigma A to the something, B to the something, C to the something, you're good. Something like this will be bad, of course, like let's say having A over B plus 1. This is bad because you can't represent this as A to the something times B to the something, right? Okay. So now we're done with that. Okay, now we'll be just solving the last example. Alright, example 5. Now we have also 3 numbers, positive numbers. We have sigma A is 1, and we need to show sigma 1 over A minus 3 is less than or equal to 2 times sigma A cube over ABC. Alright, looking at this, we have a condition, of course. This is not so clean. We need to kind of clean it and use the condition as well. Looking at this, in the point of homogenization, if you look at this, this is degree what? You have degree 3 here and degree 3 here, so this is degree 1. So this one here is actually, oh sorry, degree 0 I mean. This one is degree 0. What about this? Also degree 0. What about this? This is degree negative 1. So actually, we can simply homogenize this by making this degree 0. How? Look at the condition. You have just a degree 1 here and a 0 here. So very easy. Just multiply this by sigma A, right? And we will be done. Alright, so let's do that. So, for our solution, we will begin by saying that our inequality is the same as showing this sigma A times sigma 1 over A minus 3, and here the same things, A, B, C. And now we'll simply, okay, we can forget totally about the condition, but first let's fix this. Of course, if you expand this, it's really easy. You're going to get 3, which will cancel this 3, and you will actually get sigma symmetric A over B is less than or equal to 2 times sigma A cube over ABC. Alright, this is really cool. Now, can we apply Muirhead? Let's see. We have a sigma symmetric, and you have A over B, so that's the same as A times B to the negative 1. Cool. What about the RHS? We have 2 here. Okay, we don't want to have ABC here, we need to put it inside. So that means just we're going to have A square is good, B to the negative 1, and C to the negative 1. Okay, of course we have a 2 here, so we can delete this 2 and make this symmetric. Okay, now this is the perfect form for Muirhead. Let's just put the sequences. 1, okay, 1, negative 1, 0. And here 2, negative 1, negative 1. So now let's just check that this majorizes this. So first of all, their sum is 0, their sum is 0, that's good. Now we have 1 is, oh sorry, actually it's the opposite. We need to do this because the inequality is here in reverse. So first of all, the first condition is true. The second condition, 2 is greater than 1, that works. 2 minus 1 is 1, 1 is greater than 0, that works. And the last one is also correct. So we're done, right? By Muirhead. So this is correct and we are done. Well, actually, we messed up here. Can you catch the mistake that we did here? Actually here it is. This should be 0 and negative 1. Because always remember, you need to go in decreasing order, right? Or non-increasing order. So 1 is greater than 0, then negative 1 comes, okay? So always keep that in mind. Here, of course, it's already correct. So now we need to check it again. Of course, still the sum is 0, the sum is 0, 0 and 0 here. But let's check again. 2 is greater than 1, correct. 1 is greater than 1, okay, greater than or equal to, correct. And hence we're done. Hence indeed we have this, we have this, we have this. And of course we have the original inequality. And we're done by Muirhead. Alright, so that's it for today. Today we learned how to apply Muirhead and how it really helps us. Really, it will make our life easier because we don't need to think about the pairing system for the AMGM. We immediately just notice this and apply the Muirhead. Just one thing we should keep in mind, that Muirhead actually gives us a very nice thing because it tells us how we can sort quantities. So for example, for degree 3, you can now easily see that sigma a cube is greater than or equal to sigma a square b, that's greater than or equal to abc. Of course, we need just to fix these. So here 2, here sigma symmetric, and here 6abc. So that means we immediately can sort these. Of course, like if you're wondering what is the sequence, it should be this here, 2 1 0, and here 1 1 1. We have this majorization, So as you can see, we immediately can know this, like the sorting system between sigma a cube and sigma symmetric a square b and abc. So for example, now if we have an abc in some inequality on the lower hand side, okay, we're kind of comfortable. And if we have sigma a cube on the greater hand side, then okay, this is good. But imagine that you're solving something here and you got something like this, and you have abc here. Okay, this is kind of a warning, right? Maybe our inequality is not correct. So we need always to keep these in our minds, and this really is going to develop our basically intuition when we want to apply some inequalities, because in all inequalities they ask you prove something is greater than something, like prove a is greater than or equal to b. So you need to use some inequalities between, right? A is greater than c, maybe c is greater than d, and d is greater than b. So when we want to build these inequalities, sometimes we might use a bad inequality. So let's say b is actually greater than e. Sometimes we might do something like this. Of course, our goal is to show a is greater than b. So if we say a is greater than e now, and now okay, that means we just need to show e is greater than b. Then our inequality is wrong, right? Because actually it's not sharp enough. Okay, this is sharp, this is also sharp, but if you want to go to b, you can't go to e, right? And unfortunately, there is no guaranteed way that you can always know that okay, this is not sharp or this is sharp. You can't really know. You just need to follow your heart. And how you follow your heart. Of course, you need first of all to have some experience and kind of an intuition. Really, Muirhead is the best tool that's going to help you with that. So I really would advise you to try to play with Muirhead and try to like put these sequences and try, of course, to work with them. For example, here this is for n equals 3. Try for n equals 4, and if you want, write it in the comments below, and I will check it. I will check them and tell you whether it's correct. Okay, so this is basically our lesson for today. Alright, so as a summary, today we learned about Muirhead inequality. First of all, we started by defining the idea of majorization, and then we discussed the Muirhead's itself, Muirhead's inequality. We focused on the symmetric. Of course, Muirheads only work with symmetric. Never think about Muirheads if you have a cyclic but not symmetric inequality. So if you have something like this, prove that sigma a cube is greater than sigma a square b, and this is cyclic, not symmetric, then Muirhead will fail you, because you can't apply Muirhead here. This is not symmetric, this is just cyclic. So here, unfortunately, you need to apply AMGM, and you need to search for the pairing. For example, here the pairing is actually easy. It's just this one, and you apply it and do it with AMGM. So here, it's cyclic, not symmetric, so don't think about Muirhead. So keep this in your mind. This is one downside for Muirhead's inequality. And of course, you need to understand what is sigma symmetric, and when it is 2 times sigma cyclic and these stuff. Always keep in mind that sigma symmetric, that means you have n factorial terms. And of course, we solved some examples. Most of the examples we solved are really simple, like the standard ones, just in order for us to know what exactly is Muirhead. In the next lesson, we'll be dealing with much harder problems to see exactly how can these ones appear in some contests. Don't expect to go to a contest and receive something like this unless the contest is really easy. Okay, also here we learned that it's totally like good and totally correct to apply Muirheads for negative powers as well. And here, of course, always we can homogenize and then turn it to Muirhead. Also, it's totally correct to apply it for fractions even, right? Not necessarily integers. So here we applied it on 4 over 3, 1/3 and 1/3. And finally here we simply did the same thing, something similar. We just homogenize, always homogenize, get rid of the condition, and then have some inequality. And don't worry, you don't need to expand everything to get rid of the ABC. You can actually do that and then apply Muirhead, but you can from the beginning just do it like what we did. So both of them are correct. Just one warning, always do it in decreasing order, as we said when you write the sequences. So here, don't say 1, -1, 0, no. Alright, so basically that's it for today. So as we said, in our next video we'll be dealing with much harder examples, and we will see how exactly the Muirhead is going to help us in some math contests that are, of course, hard, like the IMO and other contests as well. Alright, I hope you guys enjoyed this video. Please like, share and subscribe to my channel, and see you guys in the next video.